Okay, now it's coming. All right, let's get started. Hello, everyone. My name is Musa, and I'm a second-year postdoc at Harvard Ophthalmology AI Lab. And for today's lecture, we are going to talk about neural networks. So let's jump into it. So for today's lecture, we are going to cover some introduction and recap for the previous lectures and class you had. Then we'll talk about the history of neural networks. And we start with the simplest feed-forward neural network known as perceptron. We'll go deeper with multi-layer perceptron, and then we'll talk about backpropagations and different architectures such as feed-forward and what kind of differences they have. Then we'll talk about activation functions, how we can initialize the weights, and also optimization algorithms, different problems with neural networks such as gradient vanishing and excluding, and also loss functions. So we are trying to cover all these topics for today. So just recap to your last week class that you had classical machine learning topic. So you should know some of these models already, like logistic regression, decision tree, random forest, SVM, KNN, and naive Bayes. And if you notice from your last week classes, these models are actually basic of machine learnings, and depending on what kind of data you have, you can choose any of these models, and whether you have supervised or unsupervised models. So also you may notice from your previous classes that machine learning has 5 core steps, including defining the problem. So the first step is you should realize what kind of problem you are dealing with, whether it's medical image analysis, classification, segmentation, or detection task, or even if it's like electronic health record. So depending on what task you are dealing with, you can go with any of those networks that you had before. Then in the next step, you needed to build the model, the actual model. And as I said, depending on whether you have supervised or unsupervised, or whether you are dealing with classification or regression, you may choose any of those models we saw in the previous slide. Then you may need to do some data preprocessing and data preparation before feeding your data into the model, machine learning model. And in the next step, you needed to train and evaluate your model. And in the last step, you need to do some fine tuning, whether you are getting your desired output or not, or you need to like going back and change some parameters and get your desired output. So these kind of steps are what you got some experience with, like in your previous classes. So this block diagram showing a general block diagram for different machine learning models that you may apply for supervised, unsupervised, or reinforcement learning tasks. So if you look at the downstream branches, you may see like classification or regression, and also you can see clustering for unsupervised. That's where you can actually choose what kind of model, depending on the problem you are looking at, you can choose. And if you notice, deep learning is always a choice with whether supervised or unsupervised learnings. So depending on if you are dealing with like a complex task, you can go with different models. But what are advantages of like using neural network compared to the classical machine learning models that you learned in the previous classes? So classical machine learning models are actually suitable for small data, if you notice, then they actually can be easily interpreted, and they also they actually don't need a high-end computational resources. You can even train it on a CPU. You don't need even like a high-end GPU. You can just use CPU, and also they are easy to implement. But on the other side, they also have some drawbacks. They cannot be applied on a large data set because they cannot like capture relationship if your data is really complex. And also they require feature engineering. You need to manually design some set of features to be fed into the model. And also they are difficult to perform on complex tasks. Like if you imagine like NLP, like natural language processing, or image segmentation. So for those kind of tasks, you definitely need more complex model rather than just classical models that you learned in the previous class. So this is where artificial intelligence and actually artificial neural network and deep learning can come in and overcome those limitations that we had with classical machine learning. So now I have one slide that leave it to you to just take a look, and based on this curve that you see on the screen, think for 1 minute and tell me what is your observation? What is the relationship between model complexity in x-axis with model effectiveness in y-axis? So you can also maybe work with your friends, and if there's any volunteer, you can just raise your hand and tell me what's your takeaway from this slide and this curve based on what we just discussed.
What's the x and y dimension? It's a little small.
Yeah, x-axis is problem complexity, and the y-axis is model effectiveness. And each curve colored, they are actually, the green is for high complex models such as deep learning. The orange is for medium complex models such as SVM and random forest, and the blue is for simple models such as linear regression and decision tree. So with this curve, what is your observation and what kind of relationship you can tell me for model complexity and model effectiveness? Any volunteer? All right. Since this is your first discussion, so I have more of this discussion. Just be ready for the following slides. We have more of these slides that you need to discuss and tell me your impression and what is your actually takeaway for those discussions that we will have in this today's class. So for this curve, you can see as model is getting complex in x-axis, the effectiveness of that model is decreasing. And this reduction is more pronounced for simple models, which are showing in blue curve, such as linear regression decision tree, compared to more complex models, such as deep learning. So that means for complex models, that's a takeaway. For complex models, you should go with deep learning models that can capture model complexity. That is what we just discussed, right, for the last slides. So let's move on. So you may notice that deep learning is itself a part of artificial neural network, just getting like more complex and more like layers you will add. Then both are underneath a broader concept of machine learning, and all of them are underneath artificial intelligence or AI. So this is kind of a well-known relationship you may see in your nowadays like when you review a paper or you just search online, you may see, this kind of diagram a lot or something similar. And talking about generative AI, which is, also maybe many of you are using like nowadays with open source chatbots like ChatGPT or any other, chatbot you use, you can just have a prompt like create an image of castle with like in middle of forest or with a fine detail for me. That's your prompt. Then you will get an output image such as what you see on the right side. And you can see, the model actually doing a pretty good job in giving you, that like your request, what you requested for a castle in the middle of a forest with a fine detail. So for this kind of task, you have like a deep learning maybe with many layers because, the image is complex. And you can even, go deeper and in another prompt ask like your model, give me the architecture of this image that you use, give me the code. So you are going kind of reverse, from the output you had to what kind of structure was used to generate that image. So another example is you can also, use generative AIs to create some mock or sample codes for you, depending on, what you need. Like, for example, in this example, it's showing it for TensorFlow. So give me a code in TensorFlow for, can be also PyTorch or any like language you need, for, 3-layer, for example, neural network. So this is kind of, just for your own understanding, like how generative AIs, can be useful in this context. So let's go through a brief history of neural networks. So neural networks, first introduced by Warren in 1943 with electrical circuits. Then following that introduction of neural networks, many other, conferences and, other researchers proposed different, variation of neural networks for different applications. And maybe, maybe one outstanding, advancement of neural network was in late 90, actually, which Jan LeCun developed CNN. He's known actually as a godfather of AI, and he has a talk today in Siri in our institute. So it's kind of by coincidence that he's coming. And so here, as a more complete, history of neural networks. So as we said, started, by neural network in electrical circuits. Then, following that, many other people proposed different models. And maybe another outstanding, advancement was, so after, LeCun, who actually introduced CNN for image processing tasks, was, different variations. For example, generative adversarial network in 2014, maybe, was another, outstanding advancement. And maybe UNet, which is, many researchers are using for image segmentation, was another, like big achievement in this AI research. And ResNet, of course, was, came after UNet. And following that, BERT actually also in 2018 was introduced for text-based analysis. And after that, GPT by OpenAI in 2020 was another big advancement in this field. And more recently, just 2 or 3 months ago, GPT-5 was introduced by OpenAI. So this is a kind of, quick history of, neural networks through history. And then if we look at, this history, AI was not interested by, all people all the time. So that is, what we call it like backlash or winters. Sometimes they call it also winters of AI. So there are some backlashes that, we can see here in this case. For 9080, for example, we had many people argued that, AI, they just didn't maybe believe in AI because that was, early stages, and they said not also even, worse to put money in it and be funded. So that was a significant pullback for funding in the US, especially. And another actually backlash was in 1993, where people, argued that AI cannot be useful for fact-based or role-based tasks because it cannot, uh, uh, make like meaningful reasoning compared to the human. So those two, times also known as winters of AI. But nowadays we know that AI is almost in any aspect of our life, and in order, to get most of it, you need actually a good hardware and software. So especially, for very complex and large data like big data, you need very good like hardware configuration and a good software to deploy that model. So going back to the first outline I showed you. So right now we are going to talk about perceptron as the simplest neural network. So if you are like going to understand what is perceptron, you can compare it to biological neuron in our brain. So just same as biological neuron in our brain, which has dendrite, cell body, axon, and terminal. In artificial neuron also, we have the same structure. So in this picture that you can see in the slide, you can see, dendrites can actually receive information, and cell body, can process and integrate those information, and then they will pass to, axon in order, to just pass to another, neuron. And also you have terminals that can be passed to another cell. So if you think of, this as a artificial neural network, so this procedure will be fired when your input signal, reaches like a certain threshold, right? Like biologically. And also, artificially, like in artificial neuron, also this is the case. And when your input signal in neural network, artificial neural network, reaching like a certain threshold, and we'll talk about what we mean by threshold, because you have those activation functions and or active threshold functions that will determine, when to fire, or pass this information that, in this case, dendrites are receiving, and in our case, like artificial neural network, your different, input layers are receiving. So let's go deeper what we mean by, all this relationship. So so if you take a closer look, you can see dendrites, in biological neurons also have like a cell body, and as we said, their job is to integrate, the input signals that are receiving as an input, and they can be fired using stimulus or impulse signal, right? When you apply that, and they can be fired, and that's when we can see an output, right? In other side, in the axon, and then, information can flow, within your network, and, you have like a connected network. And another important thing here is different creatures, they might have different number of neurons. For example, if you compare like worm with just our 300 neurons with human with around like 100 billion neurons, you can see how complex our body is in terms of having neurons and to be connected, and all these procedures that we just discussed, compared to like simple maybe model, because we are going to compare everything here with biological procedures. So let's put these two together. We just discussed artificial neurons and also biological neurons. So with artificial neurons, we mentioned that we may have like different inputs in terms of data, right? So we are talking about data in that side. And with biological neurons, we might have different biological responses, which can fire the neurons, and we can see the output, which shown in the red boxes. So the actually mathematical operations that can help us to fire this input signal in artificial neurons can be defined within the threshold function. So we'll discuss that in more detail in the next slide, what kind of threshold functions or activation, also called, they can be called activation functions, are out there that can be used to fire these inputs that we have, and in order to see a like output. And this output, as we said earlier in the class, can be different, like maybe classification tasks, regression tasks, or any other task here that you have chosen for this problem. So mathematically, your input vector, or sometimes also they can be called features. So just don't confuse. This is same like concept that you may heard, or you will see in the future or in this course. So you have like a bias term, which is just x power 0, which means just 1, and each input you have from x1 to xm, depending on the dimension of the data you are loading. And we assume we already performed some of the data preprocessing in those 5 different steps we mentioned in the first slides. So you are going to train this network, and we'll see how we can do it. And we'll have also some hands-on examples for today. So so if you look at this diagram, this is what we call it a single layer perceptron. And in the orange boxes, in the orange actually circle, you are going to do a summation of those inputs with their respective weights, right? All those weights will be multiplied, and you get a summation. And that's what we call it hyperplane, or also shown as Z. So our goal is to calculate this Z, this hyperplane, by doing that summation, and apply activation function phi to that function in order to see where we can see an output Y. So that's what we meant by that activation function. So you are going to apply this phi, which is your activation function, and to see whether it actually meets a certain criteria. So here our criteria is if Z is greater or equal to 0, you will have the Y hat, or that's is like what you are doing this calculation for, as your predicted output. So if your Z is greater or equal to 0, you will have a 1. Otherwise, you will get -1. Right? This is what we define the activation function. So the single layer perceptron also can be defined with 2 different outputs. It's not just always with one output. You can also define the single layer perceptron with 2 outputs. You have a question?
Yeah. Was the activation function the Z, or the Z being greater than or equal to 0?
So if you calculate this Z hyperplane, which is the sum of those inputs and weights, and your calculation giving you value greater or equal to 0, then your output, your predicted output would be 1, your y hat. But if you get any value which is negative, like less than 0, any value you get less than 0, then your predicted y hat would be -1. So this is what you are doing mathematically is just to calculate z. Then you just look at your criteria that you have for phi z, which we call it activation function, and you look at this criteria to see if it meets the criteria and get the output of 1, or it doesn't, and you will just assign -1 if your calculation doesn't meet the criteria that you define. And most of the time this is given to you. If it's an exam, in your case, you should have this is activation function, and your job should be to calculate z based on like some sort of weights and inputs. So yeah, we'll make it more clear in the next slides, like with more examples. So again, with generative AI, you can go and just polish your coding skills to generate like a single layer perceptron with one output or with two outputs, that we just discussed. And so another important thing here is feed-forward neural network. So we just discussed that you have a vector of inputs, and then you have some calculation in the middle to calculate the hyperplane, and then you will get output. So when you go in order from input to output, this is what we call it feed-forward neural network, right? So if you go in this direction from input to output, it means you are done with one time passing through from input to output, and that's what we call it feed-forward neural network. And it can be also it's not that easy every time, like just single layer perceptron. You can have more complex, but the concept is the same every time. If you go from input to output as a feed-forward neural network, and you may have also hidden layers if you have more complex tasks between that output layer and the input layer. You may have also hidden layers in order to capture more complex, more actually relationship or representation within your data, if your data is complex enough. So we'll talk about also these cases in the next slide. But for now, just notice we have FFN, or feed-forward neural network, when you go from input layer to the output. Yeah.
Is the hidden layer just perceptrons, like a layer of?
Each hidden layer is a neuron. We call it a neuron that will later calculate when you are going in forward direction or backward direction. We are going to calculate the updated weights on each neuron. So just if you bear with me, we'll go over all these concepts in the next slide. So right now we are just defining the basic of what we need before going to the actual example. So the activation function that we just talked about can be used to decide whether to pass that input signals you had, or not to pass that signal. So mathematically, you may have different choices for this activation function. So what we just discussed in the previous slide was the most left curve, which we call it the hard limiter. So if your calculation, like you calculate z is greater than 0 or equal to 0, then you have your output as 1, otherwise it's -1. You may have also some other activation functions. The most common one is sigmoid, which can be used for binary classification. So again, depending on the task you have, you may choose any of these activation functions. So it's not like always you go with the simplest one or with the most complicated one. You should choose a right activation function for your task. Otherwise, you are not going to get a right output, because any machine learning and neural network is like garbage in, garbage out. So if your choices or parameters are not optimized, you are not going to get the right output that you are looking for. So just know what we mean by you have many choices, but not all of them may be suitable for your case. So for sigmoid, you can see if your again, if your input signal is passing zeros, then you have 1, you have tan h, which giving you output between -1 and 1, but it's centered around 0. So maybe it's more suitable when your data is centric around 0, right? But again, depending on what kind of task you are looking for and which activation you need to use. You have rectified linear unit or ReLU, which is another common, choice for your activation function, which, many like neural network tasks, in many like tasks, you can use it for your problem. And also you have leaky ReLU, which allow small gradients to pass. That's the only difference with ReLU. So let's see. Let's imagine you have classification task, and then your goal is like binary classification. It can be also multi-class classification, not just binary output as like 0 or 1, or binary task. You may also have more than 2 classes, not just 2 class. It can this activation function also it can be applied to multi-label classifications, like especially for object detection. Within an image, you may have different labels, not just like let's say you have dog, cat, and bear images. That's multi-class classification, and you may be interested also to classify within each image like different objects. So depending on what kind of task you are using, you may go with any of these activation function. And even for regression task, when your output is continuous, not just discrete, you can also go with like linear activation functions. So maybe the most common one for multi-class classification, which can be used in the output layer, as a softmax activation. And the most common one for binary classification is a sigmoid activation. So now we have the second discussion for today. So take a look at this question and imagine you are actually dealing with a problem to classify AMD or age-related macular degeneration images, and you have a few images with no AMD. Right now we are not looking at the class of those AMD cases. And also you have like a few images with AMD, like a few patients with AMD, and a few images for patients with no AMD. So what do you think would be the right activation function based on the previous slide we just discussed? Yeah, sigmoid, right? It's obvious. So this is not kind of hard questions. It's just to make sure we are on the right track and you are following this, right? So what about task B? If you have right now different grades for AMD, so you are medical students, so I don't know which semester you are in, but let's say you have like no AMD image, you have early AMD, you have intermediate AMD, you have images with geography atrophy, you have also neurovascularization images. AMD has 5 grades. Now, which activation function should be used? Is it the only choice? Okay, yeah. I think somebody said softmax. Yeah, so let's continue. Okay, you may notice that a perceptron, because the architecture was, just simple, is good for binary classification. So what we mean by classification is you are going to assign, in this case, class C1 and C2 to your samples or your training examples, depending on, what kind of output you are getting. So if the output of perceptron is +1, then you assign, those samples that meet the criteria to class C1. Otherwise, if the predicted output, that y hat we talked about, is -1, then you assign those training examples to class C2. To make it clear, here, this graph is showing it, what we meant by, that. So first of all, you have a hyperplane Z, which that is, how you make a decision, first of all, to assign these classes. So that's, Z that you calculate mathematically. Then you have green and red dots, which are your training examples, and based on what kind of output, you get, you assign those classes, above or under, the hyperplane to class C1 and C2, right? So in order to make it even more clear, let's look at what kind of steps we have to perform, this classification, to assign class C1 and C2 to your training example. So the first step is to initialize the weights to 0 or to very small, random numbers. And then in the second step, you are going to, for each actually training example, you are going to compute the output value y hat for each training example y, and we call it z, which is inside the parentheses, and you are going to apply the activation function phi on that calculation to make a decision and classify your example to class C1 and C2, right? Depending on which activation function you are using. And then, just a recap to what we discussed in a few slides ago, you may need to update the weights, right? The choice of 0 for initialization is just your initial guess, but they are not accurate. They need to be updated. So the updating role here in neural network is delta W equal to theta, and then you have your actual y, which is also we call it ground truth, minus your predicted y, and multiply your actual input. So theta also called learning rate, and it's given to you. I mean, on the paper, for exam purposes, maybe it's given to you, but in real task, neural network task, when you are developing a network, you may need to optimize it based on your problem. So that's something also we'll talk about, because that's kind of a parameters or hyperparameters that you need to optimize for your task. So right now we just discussed one of those hyperparameters, which is theta or learning rate. Then in the last step, for train a perceptron, you need to repeat step 2. So you are going to recursively updating the weights until a certain criteria, is met. So what is this criteria is when you are minimizing the error or the distance between your actual output and the predicted y hat. So let's see how it works. So before going to the example, one more thing is, what we just discussed for updating the weights, for each of, those actually inputs, can be uh, simplified with these, equations inside the red box. So this is what we are going to use for 3 input cases. So, and also what we meant by error was you have a desired output, also called ground truth, and you have predicted, or what we calculated based on that criteria, and we call it y-hat. So if you find the error between, and there are different ways to calculate this error. It's not just always simple, y minus y-hat. You may have root square, or different like methods, you can define, to minimize this error, or in our case, you may also get like a Jacobian of, those terms, to minimize error. So we'll also cover that in the next slides. But let's look at one example to clarify what we discussed so far. So let's say we have x1 to x3, and you have also a bias term, which is 1, because x power 0, and also you have associated weights for each one. And your first task is to define your true model, or the ground truth. So if ground truth is not directly given to you, you can always look at what kind of information you have to actually get this ground truth. So in this case, the criteria is if at least 2 of the 3 input values are equal to 1, then you have a 1 as your output, like true output, or the ground truth. Otherwise, you have -1, right? So this is the criteria that we are going to use to fill, this ground truth y, and that's the first step. And you have also homework, so it's better to just if you have any question, ask it. Feel free to interrupt me, or just pay attention and make sure you are following what we are doing, because you have a homework after this. And then, so for example, for the first training example, so you have just x1 equal to 1, right? So it's not going to meet the criteria for y, and you assign -1. And you go until end of your training example, and you will get all true labels or ground truths in the fourth column for y. So now you are ready to calculate the predicted y based on those updated rows. So you have like the inputs, you will have your weights, and right now you have the ground truth. So now you are ready to calculate the hyperplane Z. So since you have x1 to x3, you can construct the hyperplane Z using this equation. It's just showing on the top of the screen. So and the activation function is, if Z is greater or equal to 0, you will get, you will assign your output as 1, otherwise it's -1. So what kind of activation is that? Is the hard limit, right? In that category we just showed in the previous slide. So now if you remember, for those 3 steps we mentioned, you need to initialize the weights, right? So you can go with 0 as your initial guess for weights W0 to W3, and we just got our true labels for ground truths, and right now your job is to calculate this Z in each step for each training example. So for example, for the first one, right, if you assign initialization values as 0 for W, and you have x1 to x3 and also y, then your calculation is ended up with, 0. And this 0, if you compare it with your activation function, is actually meeting the criteria, right? So that's why you have an predicted output of 1. Then you go until you fill all the table with the same criteria. But right now, for the second step, the difference is you need to update the weights because your first, guess for W was 0. So now for the second training example, you look at W equations, and learning rate also, is given to you as 0.1. So if you, plug in, these values into these equations for W 0 for the next step, you get, 0.1, which is the learning rate, and your actual output, which one, the ground truth actually, which one, -1 minus your predicted output, which you just got it as 1, right? So you get minus 0.2, and you have also a term of 1. It's not just showing because it's just, multiplied by 1, you get 1. And then, you will do the same for other, weights. For example, for W1, you will, for the actually second input, you will get, that calculations that we did, multiply its input. And for the last two inputs, because they are 0, you will get, no matter what the calculation is given to you, you just get 0. So for each input, you can update the weights in this way and with this updating rule. And if you do that, you just, fill the table and update the weights. So you can see, right now the weights are updating to -0.2, -0.200 compared to the initial guess of 0. So with that, you can recalculate Z. And if you recalculate Z with these values, so if you just plug in, these values, so you can get actually -0.4, and you compare it with the activation function, and since it's not meeting the criteria, you get output of -1. Is it clear? So you do the same for the other steps. For the third step, the weights again needs to be updated. And this is actually exactly what is happening, inside the code when you are training even a very large like model. The model is updating these weights for you. But it's not just, it is that easy and simple. It's just, going with more maybe calculations, but this is, what is doing it like recursively and iteratively until, and a stopping criteria is met. And for this case, again, for the third step, you update the weights, and you will look at, the previous values for Y hat and your actual ground truth and your inputs, and you just fill, the next values for all of them. So you will do the same until you reach the last training example. And once you get to the, last data, and you update all weights, you save that model, because that's when you have seen, all your data once, right? So you have seen, right now you have seen all your data once. That's what we call it also, your model is done with one epoch. So, and we assume that you already saved that, the final weights. And then if you have that final weights from the last training example, we treat it as, your initialization for the next epoch. So right now you are not going to start from 0. For the next epoch, And there's a reason why we go with the second epoch, because your model has not learned the relationship within your data. And this is, clearly shown if you look at the predicted output with the actual output. There are, many disagreements. There's a high error between, your calculated Y and the actual Y. And that's something also we call it, the stopping criteria has not met. So you go with the second epoch, you do the same for all 8 examples, but this time, you just start with, like a different initialization, and you, at the end of, the last training example, you also save the model, and you may use that for the next epoch. If you decide that, you need to continue the training and your model has not learned enough. So here in this example on the screen, we already calculated for 6 epochs. That means, your model has seen the data 6 times. So if you are training your model 6 times and you have 8 training examples, that means your total iteration is 48. And you can always, plot your training error versus iterations to see, the progress of learning. And that's, very useful, like post-processing and following your training, like to make a decision visually whether your model is good enough or not, to maybe save or maybe go back and change, some parameters and retrain. So in this case, after maybe 38, if you look at the curve, your error is going to be 0 and is continue to be 0. So that means your model is just hitting this training stop criteria, and you actually can reliably save your model. So now for your homework, you have same actually problems that we just did, but with one more input. So you have right now, you have x1 to x4 instead of just 3, you have 4, and you actually have a different definition for your true model. So this is what you should, pay attention to when you are solving this problem. So right now, y is 1 if at least 3 of 4 values are equal to 1. So you quickly, fill the table because you have that criteria for your true y, your ground truth. So you fill the table for y, right? And then for your output, which is your predicted y hat, you need to calculate this hyperplane again for 4 training examples, right? I mean, for 4 inputs and for 8 training examples. So if you do this the same, as what we just did for 3, this is exactly the same, concept. And if you understood that, this should be pretty straightforward for you. And learning rate, again, here is showing on the table as 0.1, and your initial weights are all 0. So this is for your homework. Also, there are some online tools that are very good resources for, further learning that you will, if you get these slides, you can just go to that for further information. So if you remember, I mentioned at the beginning of this lecture that learning rates or even number of epochs, are some parameters that you need to optimize for different tasks that you will actually deal with. So it's not a good idea to just go with like a random choice, random guess, and for these hyperparameters, and then back and forth, and just taking a lot of time, especially if you are dealing with a complex problem. So alternatively, if you can use some common ways to find these hyperparameters, such as grid search, random search, or use a validation data set. So Maybe another common term, if you are working with PyTorch, is Optuna, something called Optuna, for those who are interested in coding. So that's also, something that is very common to find the hyperparameters for you, and is actually assigning like some initial trials to find, these hyperparameters, and then using the optimal values for your whole training dataset. So just notice there are these common ways that you can actually find your hyperparameters and optimize them for your task. So now that we discussed single layer perceptron, let's see for more complex tasks how you can modify your architecture to be adapted with your problem. So this is what we can actually use multi-layer perceptron for. And with multi-layer perceptron, compared to the single layer perceptron, you have a hidden layer between your input and output layer. So you are going, to add more hidden layers, and you are going to capture, data complexity and representation, within your data sets by adding more layers. So you may not get, if your data is complex, it's not a good idea to just, calculate the hyperplane directly, from the input and the weight. So you should let your model, you should give your model time, to find these relationships, within your data set. And you are going to make more connections, from between your inputs and going toward your predicted output. So this is especially useful when you are dealing with non-linearity. And for large data sets, this is the case. And you have to go with multi-layer perceptron MLP. And also, if you are dealing with, arbitrary decision boundaries. So if you remember with hyperplane, we showed, the decision boundary as a linear, line to separate two different classes, right, for binary classification tests. But that's not the case always. And if you have more classes or more complex data, you cannot use a simple, linear decision boundary to separate these classes. So in order to capture, that and fitting a right model, you have to go with MLP. There are also different ways that you can actually make a decision, what kind of decision boundary, is used, and get an impression of size of your model. One of the common ways here is Vapnik-Karvenes dimension, or VC dimension. So with VC dimension, what you are going to do is to shatter your data in order to separate them to different classes. And what is the right actually boundary that you can shatter, this data to be split, into different sections or different classes with an error as low as possible. So a common rule of thumb is here is, for a perceptron with D input, your VC dimension is D+1. So this is just giving us, some impression of, what kind of architecture you can design. Like what kind of, if your problem is complex enough to go with, more hidden layers or even reduce the layers. So for feed-forward neural network with maybe more layers, the dimension is in order of W log W. And for deep neural networks, when you have more hidden layers, you have very high dimension, or those boundaries that you need to assign. And this is actually good, if you have a deep neural network, especially for complex data, but you should be careful with overfitting. Overfitting is always a problem, when you are dealing with complex data sets and complex models. And we'll discuss in more detail what we mean by overfitting and what are the ways to overcome that issue. But for now, let's look at this PC dimension. So in this table, you can see that for a single layer perceptron, your decision boundary, because it's linear, and if you apply that model to complex data sets, such as for let's say XOR problem. For that XOR problem, your class separation are in a way that, they cannot be separated using a simple, hyperplane. So you have a large error if you go with a single layer perceptron. So once your data is getting more complex and bigger, if you go with, for example, 2-layer perceptron, is going to perform a little better than, single layer with a better decision boundary, but still you have a large overlap, and again, if you add more complexity to your model, your decision boundary is going to be better and better and fitting on your classes in a better way and reducing the error, between classes, and you don't have overlap. So that means you are going to have less misclassifications, right? Later on in your classification test, if you are dealing with classification tests. So now let's focus on back propagation. So far we discussed feed-forward neural network, where you are going from input to the output layer. What about if you are going to update the weights on each single neuron in your network, and you are going backward, right, from output to input? So if you do that, that's what we call it back propagation. So if you go backward and you update the weights in that way, you are going to propagate the errors, in the backward layer by layer, and you are going to recursively computing the gradient for each neuron. So how we can do that? So for this back propagation algorithm, first of all, the common term is Jacobian, which is, square of your y hat and your actual y, and you are going to update, the weights on each neurons, using a chain rule, which is a derivative of, the Jacobian with respect to each weight that you are going in the backward direction and on each single, neuron on each layer. And you are going, to continue this process and update the weights until your error is minimized. And how you can, make a decision, that error is minimized, that's something, the optimization algorithm can do for us, which we will discuss it in the next slide. So when you are updating the weights for your neural network, you may have different issues, or your model may not perform, as you want. So if you are finding the derivative, of each neuron, and the gradient on that neuron is as you go toward your input layer, right? And the gradient of any of those neurons is getting larger and larger as you go toward the input. That's what we call it exploding gradients. And your gradients are going to go to infinity afterward. So that's not a good actually way to train that model if your gradients are going toward infinity. You should stop training and investigate the issue. And in other side, if you actually have your gradients getting smaller and smaller towards zero, right? Vice versa to what we just had for exploding. So this time is going to zero. That's what we call it vanishing gradients. So both are not good behavior for your neural network. And there are different reasons that you may see, these behaviors. The one is if your deep learning has many layers, like unnecessary layers, you just add, more complexity while your data set is not complex. If you have a poor choice for activation function, any of those functions that we just discussed, or even more, you may use, so it's not an appropriate choice, you may replace that. Or if you have a large weights or improper initialization for that initialization of weights we just discussed. And the solution to overcome these issues are whether replacing the activation function with another algorithm, or using gradient clipping, which is specifically used for exploring gradient, or a proper weight initialization, or using batch normalization, which is a common, solution to use in the neural network. So talking about optimization algorithm, so we just discussed, the weights are going to be updated, in backpropagation until you make a decision. This is the stopping point. So how you can make that decision. This is what, optimization algorithm can do is for us. So optimization algorithm actually is going to initialize the weights randomly, then it's looping until convergence by calculating the Jacobian for all samples or training examples with respect to the weight on each single neuron. And if you do that, until you are updating all weights, this is, what we call it also, gradient descent, which is very common but old method, for optimization algorithm that you can choose. So you are going to find, a minimum error, or minimize, the errors as a stopping criteria, and you are going to look at the loss or cost function. And so you have a curve that, you can look at it, and simultaneously with this, updating the gradients, you are going to look at that cost function, whether your error is minimized or not. So, but with gradient descent, because we are going to calculate this gradient for all training example is computationally intensive and super slow. For this reason, people replaced regular gradient descent with a stochastic gradient descent. And with a stochastic gradient descent, instead of calculating the gradient for all samples, you are going to get one random sample from your data, and then calculating and updating the weights on all neurons with respect to that random sample. But since it's stochastic, as the name suggests, your updated weights might not be useful for all of your neurons, because we have no idea of what kind of random sample we have chosen and whether it's the right choice. So for that reason, another common choice, which is useful for many neural networks, is adaptive momentum optimizer, or ADAM. So you may have heard this ADAM optimizer before many times. If not, you are going to hear that in this course. And it has an updating role, again similar to the gradient descent, but this time you are going to use the first moment and the second moment. And the first moment also is something we call ADAM momentum, and the second moment is root mean square propagation, and is going to use adaptive learning rates, not just as general learning rates for all of your data, to optimize all your gradients on each neuron. So this is very effective when you are dealing with a complex data and you are going to minimize your loss function. Another loss function, which is recently, I think in 2018 proposed, was actually CON. So this optimizer also was initially proposed when you are interested in decision-making process and more interpretable results. It's actually useful when you want to keep your accuracy high, and also having more flexibility in your activation functions. But it may be super slow if you don't have a good hardware in your system. So another thing here to mention is multi-objective loss functions. So so far we talked about optimizers, different optimizers, and their goal was to find the best parameters. So in this case, we talked about updating the gradients and or weights on each neuron. And the final goal was, to look at the cost or the loss function, whether, we are reaching that minimum to stop the criteria. But you may have different objective when you are training a model. It's not always, to minimize the error for classification purposes. You may be, look at a multi-objective functions. For example, minimize the error for classification, and also within each class, also look at maybe different, like maybe objects within each image in that class, and also minimize the similarity or dissimilarity between the object within that image. So if you do that and you define different multi loss functions, then you are going to combine or sum all of those losses and finally get one single loss for your task. So another problem with neural network is overfitting, as we just talk about it in the previous slide. Just a flashback to what we just said. We talked about overfitting and underfitting. Overfitting happens when your model is doing a good job on the training set, but not a good job, on the testing set. And also you have underfitting, where both training and the testing set, the performance of model on both training and testing set is poor or is very low. So if you have both of these, situations, you should go back and investigate what was the issue and how you can actually overcome that. That we will talk about, some common ways in the next slide to avoid this overfitting and underfitting. So again, if you look at this slide, you can see with overfitting, you will get when you have very complex problem with extra parameters, and you may get very good results, like maybe 98 accuracy on the training, but 60% accuracy on testing set. So that's a clear case of overfitting, and that means your model learned the relationship within the training, but is not generalizing on the testing set. So underfitting is vice versa, and that's when your model doesn't have a capacity to fully learn your data relationship, or is too simple. So if you notice, there's a trade-off here, right? To choose the right model, right parameters, and how you can design your neural network. So what are the ways to undermine the effect of underfitting and overfitting? So you can add model complexity by adding more hidden layers, more neurons, if needed. Especially, that's very important, if you have a large data, but your model is simple. So you can reduce the noise in the data, and also you can increase the duration of training, and you let the model to learn, and capture representation within the data. And in these ways, you can mitigate the effect of underfitting. For overfitting, you can add more data, or you can use K4 cross-validation, or you can use some ensemble methods or regularization techniques. So these are the ways to undermine the effect of overfitting. For regularization techniques, you can use dropout, which is randomly ignoring some neurons within your training phase, so they are not going to contribute, when you are updating the weights in backpropagations. And you are going to have early stopping. So in your code, you can assign also a criteria, not to continue training if you don't see any improvement, maybe after 5 patients, right? So that's 2 common ways that you can overcome this overfitting issue. And another way also to overcome our fitting issue is data augmentation. If you are dealing with a medical imaging task, the common ways are Philippine rotation, brightness and contrast, adjustment and cropping and zooming. And for tabular data such as electronic health record, the smoothie method is the most common way to combat this overfitting. So the last topic that I'm going to discuss for today is graph neural networks. So graph neural networks are useful when your data have like a graph structure, shape, and they have, you know, 3 different concepts. They have a node. If you look at the image on the bottom, these nodes also are entities. They can be atoms or patients. They have edges or relationship, and also they have a message passing, which is the nodes, you know, updating features by aggregating neighbor information. We have 2 common, you know, GNN networks. You whether have graph convolution networks or graph attention networks, which they can be used for different, you know, purposes. GNN is widely used in medicine, especially, which this may be something you are interested in. It can be widely used in drug discovery applications, or disease prediction, or genomics, computational histopathology, and EHR nodes. So again, you know, if you feel that, you know, GNN is the right choice here, you know, you can apply that to your problem. So that was all for today. If you have any question, feel free to ask. No question? Okay, if no question, yeah, just you, I think, had 1 homework for today. That yeah, you, I don't know how you should submit, but that's something, you know, you had in the lecture slides that need to be solved by hand. But it's not something difficult. And feel free, you know, to email me if you have any question, you know, to solve that homework. My email is on the screen. All right, I'm going to stop sharing and